Hello everyone. Today we will present upper body thermal referral and tactile masking for localized feedback. This work was done in collaboration with Hyungi Son from ETRI and my students Haokun Wang and Yathar Singhal at the University of Texas at Dallas. My name is Jin Ryong Kim. Thermal sensation is essential in immersive VR as providing multisensory experience can further enhance the user experience and increase the presence. There are many scenarios where users need to interact with the thermal feedback. For example, traveling in high temperature areas like desert or fire scene where you can feel hot with extreme heat. Our work is focused on how to deliver localized thermal feedback in a large-scale display using a low-cost approach. In fact, there are several approaches to provide localized thermal feedback through heat conduction by placing a thermal sources on the body part using thermal devices like Peltier, airbags, or water pipe with hot liquid. People also use non-contact approach using IR projectors to provide a thermal sensations to the body surface. Those thermal displays have high complexity in setup, requires a large number of components, and a high power consumption to deploy in a large-scale application. Achieving localized thermal sensation brings a lot of challenges. Thermal actuators are very expensive compared to vibrotactile actuators. They are difficult to scale to a large body size because of their high power consumption. And thermal actuators have slower activation time, and also human thermal perception is typically slower than vibrotactile perception. So we came up with two main research questions here. One is, can we provide localized thermal feedback on a large scale body part efficiently and cost effectively? Two, can we solve this engineering problem with perception-based approach?
Our approach is based on the combination of two illusionary effects. First illusion is thermal referral, which is cross-modal interaction of referring thermal sensations to a nearby location. For example, when thermal stimulus is presented on both the index finger and ring finger, while the middle finger is kept thermally neutral, thermal sensations are perceived on all the three fingers. That is, the thermal sensations from those index and ring fingers are referred to the middle finger. Second illusion is tactile masking. Whenever two tactile stimuli of different intensities are presented to two nearby locations, the stronger stimulus dominates the weaker stimulus, resulting in perception of the stronger sensation. For example, when a stronger stimulus is presented on the index finger and a weaker stimulus on the middle finger, tactile stimulus is perceived on the index finger. By combining these two illusions, it is possible to provide perceptually localized thermal sensations on a larger body area such as human's back. When thermal and tactile actuators are activated simultaneously, thermal sensations are migrated to the location of the stronger tactile feedback due to thermal referral, while the thermal sensations on the original location are masked by the referred thermal sensations at the stronger tactile site. This results in perception of localized thermal feedback on the referred site. We present these localized thermal sensations through an adjustable thermotactile vest. This setup is meant to cover majority of users' back. This vest has 16 ERM vibrotactile actuators placed in a 4x4 array. In between the second and the third column, 4 thermal actuators are vertically integrated. All these actuators are connected to a central command system via Bluetooth. Localization of thermal cues can be controlled by activating the vibrotactile and its corresponding thermal actuator. Here, we show characteristics of actuators used in our approach. The thermal actuator can achieve 50 degrees Celsius in 3 seconds with a power consumption of 2.68 watts. We vary the vibrotactile actuator's intensity while keeping a constant frequency of 125 Hz. The power consumption for a single vibrotactile actuator is 0.96 watt, which is almost 180% less than that of a thermal actuator.
We designed two user studies. User study 1 aims to evaluate the feasibility of our approach. And user study 2 aims to evaluate our approach by comparing it with thermal-only conditions in VR. Now let's take a look at our user study 1. The goal is to validate our perception-based approach. We designed a within-subject study with 10 conditions per each row, activating a combination of Weber tactile actuators and thermal actuators. We have 4 single conditions, meaning we activate 1 actuator at a time for each row, and we have 3 double conditions, activating 2 actuators at a time for each row, and we have 2 triple conditions, activating 3 actuators at a time for each row, and finally, we have 1 quadruple condition, activating all 4 actuators at a time for each row. Thermal actuators are placed in the middle of each row and activated together with the Weber tactile actuators. This yields a total of 40 conditions with random orders, which covers all tactile areas on the west. We recruited 16 participants and asked them to wear the vests and mark the perceived thermal area on a tablet once they perceived the thermal tactile sensations through the vest. We superimposed all participants' joints and got a result which shows the perceived thermal area distribution. As can be seen, higher intensity of the red color indicates more overlapped responses, which shows the area perceived by more number of participants. We clearly observed that most of the concentrated areas were well matched with the Weber tactile locations, suggesting thermal referral illusions occurred on the upper body.
Let's look at study 2. The goal of this study is to evaluate our approach by comparing it with the thermal-only condition in VR. There are 3 conditions. The first condition is thermal-only with the 4 thermal actuators. This condition, we place the 4 thermal actuators in the middle of the vest. The second condition is thermal-only with the 8 thermal actuators. In this condition, we place the 8 thermal actuators in 2 columns in the middle. The third condition is thermal tactile with the 4 thermal actuators, which is the combination of the thermal and vibrotactile actuators. This is our approach. We recruited 16 participants. In the experiment, we provide a visual cue of the frame in random order at 16 locations. We also provide sensation that match the location of the visual cues. The participant's task is to pull the trigger as soon as they perceive the heat sensation. We measure the position time, location accuracy, and preference ratings. We observe that thermal tactile condition shows the shortest process time, and thermal-only condition with 4 thermal actuator shows the longest time. Thermal tactile shows a significant difference from two other conditions. It was clearly observed that vibrotactile feedback help user to perceive heat. In location accuracy, both thermal tactile 4 and thermal-only 8 achieve over 19% of location accuracy. Thermal tactile 4 condition shows significant from thermal-only 4 condition.
We presented a unique approach to achieve localized thermal feedback using thermal referral and tactile masking through interplaying thermal and tactile cues. We believe that our approach is simple but very powerful to solving engineering problems by leveraging humans' perception. We clearly show that our approach is cost-effective solution with significantly low power consumption. We also show that our approach is promising for designing thermal wearable devices to provide a localized feedback. Thank you for listening to our talk, and please let us know if you have any questions.